neutrino nucleus scattering, so on CEvNS. And the speaker will be Strigari. And Louis is working at the Texas A&M University, and he is involved on searches in new physics, both in neutrinos, but also in indirect dark matter searches. And so he will give an overview talk that then is also a good introduction to our third neutrino panel.
Thank you. So actually, can I share my,
yeah.
Okay.
Wanted to ask, so I can see your camera.
Okay, good. Thank you. I see. Hey, you can see.
But the slides are not up yet. Yeah.
So I'll go into presentation mode. I trust that looks good.
Yeah, that looks good.
Okay, great. So, okay, so thanks for the introduction. It's a pleasure here to talk about coherent neutrino nucleus elastic. Actually, I forgot there's an elastic in there, but coherent elastic neutrino nucleus scattering, or CEvNS for short. So this will be an overview talk about all the science that's going on in this topic, and I hope to convince you this is a really exciting topic in neutrino physics, and high energy physics and astrophysics and nuclear physics these days. And there's lots of interesting experimental work going on and lots of interesting theory that accompanies that experimental work. So we don't have too much time here to talk, so I'll be a little bit brief in my overview, but I'm happy to answer questions on Slack afterwards and have further discussion. So let's start off really basic. Of course, this is a picture of neutrino interactions over sort of the large scales of energies that we've considered them at this point. We now have detections of neutrinos over vast energy scales through many different processes. So of course, extragalactic high energy neutrinos are now being detected from distant sources. Terrestrial sources detect neutrinos at so-called intermediate energies, GeV's scale or so, via accelerators and through the atmosphere. Going down to lower energies, we've of course seen neutrinos from supernova, the sun, as well as from nuclear reactors. So these are sort of neutrinos in the MeV-ish energy range. And of course, we can even go down further and talk about neutrinos from the Earth itself. So-called geoneutrinos, as well as even much lower energy neutrinos from the Big Bang. So this is the focus of my talk here will be kind of this energy range here of, say 1 to hundreds of mega electron volts. So we're going to be studying neutrinos from both terrestrial sources and astrophysical sources over this energy scale. Okay, so in particular, at this energy scale, I'm going to discuss the CEvNS process, coherent elastic neutrino nucleus scattering, or CEvNS for short, as it's become known. So really the question is what is CEvNS and why is it interesting, amongst all neutrino scattering processes and really, amongst processes at these energy scales? Well, fundamentally, CEvNS is due to neutral current interaction between neutrinos and quarks. Due to the nature of standard model couplings, there's a coherent enhancement to the cross-section due to the scattering on neutrons itself. And this cross-section gets enhanced by the number of neutrons squared. So the total scattering amplitude is the sum of that on constituent nucleons. So you can kind of see that this is why it's coherent, in a sense, coherent on the neutrons in the nucleus. This process requires a small momentum transfer relative to the size of the nuclear target. And that's, of course, where you get the coherent enhancement from. So this n squared factor actually makes this total cross-section very large. But the long-standing issue with CEvNS is that there's a small amount of energy that gets deposited to the nucleus of order kiloelectron volts or so. So that actually has made it difficult to detect. So you can kind of compare the CEvNS process, the cross-sections for CEvNS as a function of neutrino energy relative to other processes at these energy scales, inelastic processes, for example, in argon, neutrino electron scattering processes as well. So the CEvNS here is a much larger total cross-section, but it is, but like I said, in terms of detection, it's been proven to be difficult, even though, as you can see here, it's postulated to the first calculation of the CEvNS process was done in the early 1970s. Okay, but nonetheless, we are making progress. The overview of this talk going forward here is kind of the three main sources, neutrino sources that are used for SEvNS. Sort of accelerators, and the main accelerator these days is the coherent experiment. I'll start talking about that, as well as we'll use sources, reactor sources, neutrinos produced at various reactors across the world. That's also a source of SEvNS. And we'll also talk about astrophysical sources and what we can learn about neutrinos from these sources, as well as properties of the sources themselves. Okay, so let's kind of start off. Like I said, SEvNS was first postulated to be detected in the early 1970s. Only a few years ago was it actually experimentally identified, and so it was experimentally identified by the coherent experiment, which uses a stopped pion source at the spallation neutron source at the Oak Ridge National Laboratory. Okay, so the neutrinos that get produced at the coherent experiment here at SNS are due to pion decay at rest. And here you can see the neutrino spectrum from pion decay at rest. So you have so here's the decay at rest components here. So you can kind of see two sort of key pieces of the spectrum. There's the so-called prompt neutrinos, which come from pion decays. And that's indicated here by the red peak. And also there's a so-called delay component, which comes from a delayed muon decay. And you get muon antineutrinos as well as electron neutrinos from this delayed muon distribution. So you have different flavor components of this flux, which actually makes it a really interesting source in terms of examining different types of neutrino properties. So in 2017, the coherent experiment actually published the first detection of the SEvNS process. They used a cesium target, as indicated here, and they measured the SEvNS cross section to be pretty much consistent with what is expected in the standard model. So you can kind of see what the predicted cross section is here for SEvNS as a function of the neutron number. The standard model predictions are more or less in agreement. There's some a discussion about how to handle the nuclear form factors in these calculations. We'll get to those in a minute, but more or less we're consistent with the standard model. Coherent actually followed up that detection of SEvNS with detection on a larger target, liquid argon, a single phase liquid argon detector. So this was announced within the past year or so, the so-called CEvNS-10. So they identified the SEvNS process here on argon, and once again they determined it to be pretty well consistent with the standard model prediction. So we've got two detections now over sort of a scale of neutron numbers. We've shown here a couple of other targets which are being considered and for these types of experiments going forward. And sort of the goal here, of course, is to really map this cross section out as a function of neutron number to see if the predictions match the standard model across these neutron scales. So there's been an enormous amount of literature that's actually followed up on the coherent results, and the coherent results have had incredible scientific impact on the neutrino community and sort of the BSM high energy physics community at large. So here's as much as I could condense the BSM literature into one slide here. There's of course many ideas that have followed up and to examine these results. So one particular result, of course, is the case of non-standard neutrino interactions, and you can generate non-standard neutrino interactions via processes here, which I've diagrammed here on your left. So you can imagine there's some new physics at a high energy scale, which generates a heavy Z prime, and you can motivate these heavy mediators and parameterize them with effective field theories. You can also generate light degrees of freedom, and that can be used to generate non-standard neutrino interactions, and sort of different types of mediators across a whole wide range of energy scales can be used to generate these NSIs, and they can be constrained by these SEvNS types of experiments. So SEvNS is actually unique in terms of constraining NSI parameters, because it's so here's the sort of standard parameterization for these NSI couplings. So SEvNS is unique in the sense that it can sort of split the up and down components of these couplings, which is difficult to do for other experimental probes that are using that study non-standard neutrino interactions. Okay, so this is just a little hint of what one can do for BSM physics. There's also, as I mentioned earlier, some you have to understand sort of nuclear structure to get the form factors right, to get the SEvNS cross-section entirely correct. The interesting thing about the SEvNS process itself is that actually it kind of gives us one of the first direct measurements of the neutron distribution in the nucleus. So the size of the neutron cloud, if you will. So using the actual coherent results themselves, we actually get a measurement of the size of the neutron distribution here. It's order 5 Fermi or so according to the current results. In addition to understanding sort of the nuclear structure behind SEvNS, of course, there's radiative processes and higher order effects. There's non-coherent spin dependent components which ultimately have to be understood. But really, that's kind of nailing down the cross section. So at the percent level or so, right now, we've kind of just mapped out that SEvNS is there, and we're just sort of at the initial phase of trying to really understand what goes into this. Okay, so in addition to accelerators like coherent, nuclear reactors are aiming to detect SEvNS. So there's many programs across the world, a handful of here are shown on the slide, to try to detect SEvNS using a variety of nuclear reactor sources around the world. These reactors range anywhere from gigawatts or so down to sort of smaller megawatt research reactors. And sort of here's a cartoon, of course, of how the neutrinos are generated, say through uranium-235 fission processes. And of course, these neutrinos are electron anti-neutrinos that come from the reactors. The unique aspect of reactors sources for SEvNS is that they produce neutrinos at a characteristically lower energy scale. So whereas for an accelerator source, it might be neutrinos might come in the average energies of tens of mega electron volts. Reactors tend to be mega electron volt or so neutrino energy. So this actually is interesting because it gives us a way to study SEvNS at a different energy scale, okay, and see if there's any, study the constraints on BSM physics, for example, at different energy scales. So speaking of BSM physics, one often talked about way to use SEvNS with reactors is to search for presence of possible sterile neutrinos. Of course, there's been lots of discussion in the past, several decades about hints of electron volt scale sterile neutrinos via some experiments that have been done, LSND, mini Boone. Some solar neutrino data may be consistent with be interpreted as indicating the presence of sterile neutrinos. It's of course unclear, when you put this whole picture together, whether this EV scale sterile neutrino fits the data the best. The interesting point here is that if you can actually use the SEvNS process to say look for with reactors and accelerators, say to look for neutrino disappearance, because in the standard model it's a flavor blind process. So you can actually use that to study sterile neutrinos, and there's been a variety of literature that has been used to examine this process here. And here's an example of constraints you can get, say, with projected future SEvNS experiments compared to sort of the best fitting regions from several experiments around the world. Okay, so reactors and accelerators can be combined to provide good constraints on BSM physics in the form of sterile neutrinos. So let me move on to talk about the third source of SEvNS, which I mentioned earlier, which is astrophysical sources. And of course, this has a nice sort of tie-in with sort of search for dark matter and direct searches for dark matter. So here's, of course, a picture of what we believe our Milky Way looks like in dark matter. And if dark matter is in the form of a WIMP, or weakly interacting massive particle, it can make a signal in a detector very much like SEvNS would, in the sense that you get a low energy recoil that has where about a few kilo electron volts of energy is deposited into the nucleus. So here's a figure here that's getting out of date pretty quickly, but so from the previous SNOMAS process, which shows the constraint on spin-independent cross-section for WIMPs as a function of time. And you can kind of see we're really gaining a lot of ground here in terms of placing good constraints on the WIMP cross-section. So these detectors, so G1, G2, G3 here sort of means the scale of the detector, that is the generation of the detector that would be used for studying the WIMPs. But of course, once you get down to a low enough cross section in dark matter, you actually start to compete with coherent neutrino scattering signals from different astrophysical sources. So if you're searching for dark matter, this is a background, right? If you're searching for neutrinos, it's a signal. So let's try to think about this as a signal here. So what are the astrophysical sources that we need to worry about? The main ones are the sun, neutrinos from the sun, neutrinos from the atmosphere, and neutrinos ultimately possibly from supernova as well. So we had a nice overview talk yesterday about the solar neutrino program and what has been done really in the past half century or so in that program to help study the properties of the sun as well as neutrinos that come from them. So yeah, atmospheric neutrinos come at a little bit higher energies. So here's a relatively recent spectrum of atmospheric neutrinos sort of over the entire energy scale at which they're detected. And then here's a spectrum. So here's a picture here of the supernova 1987A and the neutrino burst that came from that. Also, in principle, we could, with a large enough detector, as indicated here, detect CEvNS through the diffuse supernova neutrino background. So what I'm going to do here in the next couple slides is I'm going to focus on just neutrinos from the sun and the atmosphere. And for supernova type studies, I'll refer you to these references that I have here. Okay. So let's talk first about neutrinos from the sun. Okay, so here's the neutrino floor that results from the coherent scattering of solar neutrinos as well as atmospheric neutrinos and possibly the diffuse supernova neutrinos. So down, once you get to these scales of cross section, that's where a dark matter experiments start to compete with neutrinos from these sources. So, when this issue was first discussed, now going back a decade or so ago, the neutrino floor seemed kind of like a little bit of a long way away. But actually, it's right here because the most recent xenon results have pushed their thresholds down to about kiloelectron volt scales, really understood their systematics at these energies. So now they're really close to actually being able to detect the boron 8 component of the solar neutrino flux. And you can kind of see at this sort of zoomed out low energy scale for dark matter here, sort of in the range of 1 to 10-ish gigaelectron volts. You see this peak here due to boron 8. So dark matter experiments are now really closing in on getting a measurement of the boron 8 neutrino flux. And you can actually get, at the moment, decently, using the boron 8 flux from solar neutrinos, you can actually get a good, a decently competitive constraint on non-standard neutrino interactions. So we're getting to that scale there. And I think, in the next 5 to 10 years, I think we'll continue to make progress. I think we'll, likely look forward to a detection here in going forward. Okay, so what types of detectors are we specifically talking about? So here's kind of the range of dark matter detectors that have been used over the past couple decades. So here's kind of just a particular focus on xenon detectors. Also, there's an argon program and a germanium program. So right now we're sort of at the xenon n-ton scale. So that's the scale that I showed earlier that came pretty close to detecting boron 8 solar neutrinos. Probably the next generation, which certainly will nail them, is these G3 type experiments, which are larger scale, sort of tens of ton scale xenon detectors, and that really will become not only a dark matter observatory but certainly a neutrino observatory as well. Okay, so I mentioned earlier we had to talk about solar neutrinos, so I won't go into too much detail about what we've learned here on these. So here's just some recent highlights of the solar neutrino program. So Boraxino results are shown here. So these Boraxino detections come from neutrino electron scattering from electron flavored and some muon flavored neutrino or electron flavored neutrinos from the sun. Of course, very interesting thing is that recently Boraxino detected the CNO component of the solar neutrino flux via a multi-component analysis. However, these Boraxino plus other solar neutrino data is still really unable to distinguish between so-called low metallicity and high metallicity solar neutrino models, right? So for this, ideally, one would need a neutral current experiment, and that's exactly what CEvNS gives you. So measurement of this neutral current component, this full neutral current component of the boron 8 spectrum in a dark matter detector would help directly probe the solar metallicity and possibly sort of break this degeneracy. So you have this sort of low metallicity solution, you have this high metallicity solution, and you have kind of data here. And this was an analysis done by Borexino. So this would be immediate, actually. So this would kind of give us, in some sense, the second, full neutral current detection of the boronate component of the solar neutrino flux, independent of the SNO measurement. And of course, it's a different scattering process relative to what how SNO measured their neutrinos. So this is something to really look forward to. And, this gets back to this idea of, not only learning properties of neutrinos from the sun, but also learning, what's going on in the solar interior, the metallicity structure of the solar interior, which is, not straightforward in some senses to obtain from the interpret from the astronomical data. Okay. I should also mention you can actually use solar neutrinos to bound non-standard interactions in stereo neutrinos as well. Okay, so neutrinos from the atmosphere. There's been a little bit of work that's been done on this topic recently. Okay, so I showed a picture of the atmospheric neutrino spectrum. So I said we mentioned that it scales, up to very high energies down to energies of giga-electron-volts or so and below. So the lowest energy measurements, the atmospheric neutrino spectrum we have come from Super Kamiokande. So if we're talking about a dark matter detector and we're talking about CEvNS from a dark matter detector, we're actually sensitive to neutrinos at much lower at lower energies than we're seen by Super Kamiokande. You can kind of see that here in this figure here. So if you if you focus in on say a generation 3 xenon detector, you see this blue curve here, and compare that to, so this is the distribution of neutrino energies that you'd be sensitive to in this type of detector compared to what the distribution of energies that Super K is sensitive to. So really understanding this really requires understanding the systematics of the atmospheric neutrino flux at these very low energies. And there's lots of interesting physics that goes on here, that modulates the cosmic ray flux at low energies and therefore modulates the atmospheric neutrino flux. So really understanding precisely, where that neutrino floor is and, mapping out when we get there, not only may depend upon, types of non-standard neutrino interactions, it's also going to depend on really precisely mapping out that the flux and understanding the different processes which how cosmic rays they propagate and make it to the Earth and create neutrinos ultimately. Okay, and there's been some work on this front as well as there's been some work on using neutrinos to atmospheric neutrinos in future detectors to study non-standard interactions as indicated here. Okay, so here's kind of what it would look like. This kind of wraps it up a little bit in terms of dark matter detection. You have a neutrino or dark matter particle come in, make an interaction. You have the neutrino or dark matter particle coming out. You make a so-called S1 signal, then an S2 signal, and the S1 signal is plotted here, the S2 signal is plotted here, and sort of the different components of the neutrino that neutrinos that we're studying, say boronate solar neutrinos, atmospheric neutrinos, they kind of live in different regions of this S1, S2 space. And you have some leakage from electron type scattering events where neutrinos scatter off electrons. So these would be PP solar neutrinos scattering off electrons to make these types of events in the detector. So really understanding sort of all these components from an experimental perspective, understand, we have to do a full likelihood analysis. Really, extracting these signals is actually going to be a bit of a challenge. And this kind of tells you the scale and the scope of what that challenge is. And this was examined in some recent papers about how to do this and how to extract these different components of the flux, given what we might expect how a generation 3 type detector might work. Okay. Okay, so kind of tying it together, I've only got a couple minutes left here. Oops. So you can actually combine the terrestrial measurements with the astrophysical measurements to get, kind of a picture of, what CEvNS can do. And sort of one example about that in terms of studying BSN physics is the so-called dark side of the solar neutrino parameter space. So we think of sort of the solar, mixing angle and mass splitting. We kind of think in terms of this parameter space here, as indicated, CAMLAN and solar data, and combining them gives us a constraint on delta M squared as well as theta 1, 2. There's also this sort of well-studied dark side solution of the solar neutrino problem. And if very briefly, if you have large NSI type couplings, you can actually still allow the so-called dark side of the solution where you change the octant of the solar neutrino angle and the sign of the mass ordering. CEvNS is actually interesting because it actually lifts the degeneracy in studying these NSIs and dark side parameter space. And you can kind of see that here. So here's kind of sort of the band is the standard LMA solution. And this LMA dark here is where this LMA dark lives with sort of large non-standard neutrino interactions. Sort of this blobby region sort of tells you where a coherent is able to constrain in this parameter space. You can kind of see this degeneracy gets lifted because this coherent scattering experiments are sort of different in the sense from an oscillation type experiment. Okay, so I focused on sort of the three main sources to study neutrinos. In the last minute or two, I want to just add a little bit of a twist to the game here. So, CEvNS has turned out to be a very interesting process. It's been very fruitful and, theoretically and experimentally. So, how far can we push this? So one idea that we've been thinking about in the past year or so is, can you study CEvNS with so-called directional detectors, where you not only detect the energy deposited into the nucleus, but also, say, the sense of recoil of direction of the nucleus. So this is sort of a standard discussion in the dark matter direct detection community, where you want to, of course, detect the direction of the nucleus, because you know that you know where the dark matter comes from, and you can eliminate backgrounds. Well, it turns out you might be able to repurpose these types of detectors to do CEvNS with them. Here's the angular distribution of the nuclear recoil relative to the incoming neutrino, say for a source, an accelerator source like coherent. You kind of see it as a peak for a couple different targets. Due to the kinematics, the reactor, the shapes of the spectrum will be a little bit different. So this is actually an interesting way to think about combining these types of measurements. We can actually deploy a directional detector at either, say, SNS or a reactor to get this directional information and propagate that forward to try to identify VSM signals, such as NSI. So sort of, for example, if you had a vector-like mediator, you get sort of a large peak here due to the kinematics at a relatively low nuclear recoil relative to the incoming neutrino beam. And so that actually is distinct from the standard model. So if you're talking about trying to really identify, say, a VSM process, this type of detector would be really useful. So we actually recently did an analysis. So one particular type of directional dark matter detector was the drift detector, which was a low pressure TPC. And we did a recent examination how that would do if you put this into a larger, slightly larger energy neutrino beam line at Fermilab, thinking about sort of the low energy tail of neutrinos that come from that, and if you could actually use that to study CEvNS. So here's sort of the characteristic energy scales that you'd be sensitive to through CEvNS. So you could do that. This actually makes a good, with some reasonable with realistic technology these days, you can actually get detections, with these types of detectors. You can actually study, not only beyond the standard model processes, but weak mixing angle constraints at different energy scales as well. So I'm sorry, I'm running a little bit late on time here. So I've got a couple of just summary slides here. So here's a figure where we are in terms of the cross section versus the neutron number. We have accelerator sources, we have reactor sources, we have astrophysical sources, and we have detection. We have now 2 detections: argon, cesium, xenon, germanium, and sodium are targets that we have upper limits for. We're continuing this process. There's many CEvNS experiments going on around the world, both reactors and accelerators. So here's a map of them. And so here's sort of a timeline of what we might expect for different CEvNS detectors that at least we've been able to chronicle at this stage. There's probably many more that aren't even on here. So I hope that I've convinced you this is an exciting time for this field. And I'll take questions now. Sorry, I'm running a little late.
Thanks, Luis. It was really truly an excellent talk. So as before, the participants can insert their questions via the Q&A field. I had a question about the middle of the talk when you were talking about this uncertainties that come in from knowing the form factors of the nuclei versus the cross sections. So can you quantify a bit for the current level of coherent results? What is the contribution of the form factors to?
Yeah, that's a good question. So right now, just the short answer is it's a few percent level. What one does is typically use different models for the form factor. So coherent is, let's see, where do we go here? So coherent, like we discussed, neutrinos are a little bit higher energy, so you do have to worry about the effect of a form factor in there. But yeah, it's kind of like where at these sort of momentum transfers one talks about sort of these we're not sort of at you're kind of at the area where the Q squared dependence, you haven't kind of hit your first dip, right, in the form factor. So really, like, all the sort of reasonable models that study form factors at these sort of momentum transfer scales, there's really a relatively small amount of systematic that goes on in there. You can parameterize the form factor via different types of models, Helm form factors. There's actually more formal EFT analysis that's been done by, I believe, the set of authors here to study the behavior of CEvNS and nuclear effects in CEvNS sort of at these energy scales. But I think right now, I think it's fair to say for this, maybe a 5 to 10% level. I forget the exact numbers. I can't remember off the top of my head, but it's something in that ballpark. Of course, if we would go to higher energies, we'd have to worry about higher energies and sort of keep these same heavy targets. We'd have to then we'd have to understand probably the form factors in a little more detail. Of course, if you go to reactors, then it's less of an issue. Yeah, okay. That's a really good question and kind of ties in all together, like the how you got to understand nuclear physics and all the other everything for this process to really nail it. It's a good question.
But on the other hand, this means if you try to measure solar neutrinos with this, form factors are also not so much of an issue. But
form factors essentially matter zero, yeah, for solar neutrinos, because the corresponding momentum transfers are really for the types of targets that we're considering. The momentum transfers are small enough, yeah. So in that sense, you're kind of in a sense fully coherent, right, in that regime. But even for the these coherent results, it's still pretty robust, right?
Okay.